the computer. Okay, okay, so now for the record, today we will talk about the laboratory number 4, about the task and the scheme you need to develop by yourself, and what you need to do to model and to analyze. So first of all, in Ortus, you have the description for task number 4, this one. Okay, I open this task. Okay, this is your task number 4. And what do we see here? So this is the same idea as for the lab number 1, when we have a concentrated power system implementation with one type of generator and all load connected to the one bus. The main difference is that in the lab number 1 you have a hydropower plant type generation, this part. For this example, for you, this is CHPP type generator. What is more? I just want to highlight this moment that task number 4 contains from two similar parts. So we model everything the same with one difference. So this is when we have power generation, power generated by CHPPs, and this one, you see this number 4.1, and here 4.2 when the power is generated by hydro. And the last one, mix. Okay, we could, how to say, here just for you, I separated all these steps to be clear and more easy to complete this task, but physically, so we have first one with CHPP, the second one with hydro, and the last step is when we make a mix. So we connect both. This is very easy. We just take this part, copy and paste. So this physically, this is scheme number 3, but idea is we just copy two types of generator here. This one, this copy paste, and this one copy paste. Okay, this is just about the structure. Now let's go through step by step, and let's start with the first one. So 4.1, so we design an under frequency load shedding automation for a power system represented by a concentrated model, like in the first lab. So first one is with, okay, I'll zoom in. We've represented with CHPP. So that means that we have two different transfer functions that represents what is the difference between CHPP and hydro. We understand hydro, we have a turbine that water turbine rotates a generator. Here we have a steam turbine that rotates a generator. And so steam turbine have different little bit parameters. As a result, that we have different control for the steam flow instead of the water flow for hydro. That's why we have this difference, yes? And this difference are represented by different transfer function. This for your use, number 5 and number 6. To simplify your task, we could use two similar transfer functions for both. Here you could see number 5, a periodic transfer. Okay, there's some mistakes because it was written, how to say, without any correction, just during the lab. So, a periodic transfer function to represent the valve, the valve motor for steam flow. So, this one. And the second one is number 5 to represent power from steam turbine to generator transfer power. So, as I mentioned, you could use the same values as you can see here. So, transfer function with the only one parameter. This is time constant, 0.25 seconds. Yes, for transfer function. This is to represent CHPP, the difference. And one more difference is block number 11. Because in your first lab, there is no saturation block here. Why? Because for the first lab, when we analyze what is going on, if you started to do your task number 1, you could find a very interesting conclusion that if you make a power outage in percent, that is here. No, this is block number 3. It's a step function in Simulink, yes. So this is the same in the first lab. So you have two values, two variables. So time moment when this outage appears and the value. The value is in relative units, so it means that we could say that this is in percent. So from 0 to 1. So 1 is 100%. If we use for the first lab for analysis, for example, the outage of 50% or 60%, we find that we have a huge frequency drop, but there is no a blackout. So whatever outage we have, system will survive. No, I think this is more right word. So why? Because we don't have the block that represents the limit of power for a power generator. This is for the first lab, for the very beginning. Now we have more knowledge and we could fulfill this scheme and make it more correct. So to be more correct, we need to put this saturation in other words, it's a limiter that limits the power for this HPP. That's why it has the upper limit and the lower limit, yeah? No, typically, because it's saturation is this block, it calls saturation, so limits. It's a structure that it have upper and lower limit. What we understand, okay, but in real life, so what is the lower limit? We don't have this lower limit typically, yes, but we have the upper limit because we could generate more, but it is possible from our generator. That's why for the block number 11, here we have 5% up and down. This is, okay, I'll say you the truth. This is wrong. 0.95. But this is made specially for student to push, how to say, you to analyze the situation. Because when you put these values, you will find that you have problems with fluctuation after the fault. Why? Because you have a limit for power drop and you could not follow this fluctuation to stop them. This is a typical problem when a really powerful fault appears, when we have lost a lot of power in different part of power system, such asynchronous problems. This is how to say the definition, that we have different parts of our power system, as I explained to you previously, that we have with over generation, and we have parts with not enough power because we can't transfer this power due to the problems in power system and faults and so on. Yes, so we have different how to say problems with frequency. That's why, just to highlight this moment, in this description there is this value for you to put the wrong value and to start analyze what's going on, what this scheme is not working. But okay, to simplify your life, I said that I just explained the situation that physically, yes, we have the limit of power because we can't produce more that we have, yeah, but we can stop the production. We can lower. The lowest possible power is 0. Okay, this is for this. Everything else, this is our statism about this, our regulation possibilities. This is power system inertia. This is the load reaction, base frequency. Everything is the same. Maybe 2 moments. Here you could see step. No, it calls this function in the Simulink. This is step generator. This is step, and this one is the step. As I said, this is for the power outage. So what power outage in what second? This is a step function. Yes, in your first lab there was only one this block about this outage, but for this work to have more options to analyze how your auto frequency load shedding automation is good or not, to analyze this, I decided to put this one more. So what is your task? To make a series outages, so series faults. So in, for example, time moment 2 seconds, the first one appears, and in, for example, 5 seconds, another one. And to see what will happen if we have serious problems, serious faults, serious power outages. This is about the power system schemes. And what is new? This block, under frequency automation block, which task is to analyze the frequency and to disconnect load if we have problem with balance. In other words, when we have a frequency drop. Okay, this is transfer function explanation. This is the second one for CHPP. For CHPP, there are 2 options. You just can copy from the laboratory number 1 and to paste here, or you could simplify. You see, this block number 4 is a simplified version of 2 series blocks from the first lab. This is, how to say, for your choice. You could keep this block like it is here, or you could just copy paste, because you see, okay, yeah, this is the same as the lab. This number 3 is the same as your lab. Yeah, the only difference we could see here, how it is represented. 2 and 4 This is 2 and 4, or like it is in the first lab. So you could compare these two schemes and choose what you want. So this part is the same. Okay, now for about this under frequency automation, how we design this block. No, typically very simple. As you remember, I described you and we saw in the book that the idea is we have different stages with different set points. Typically, in a simplified way, we have two set points. Set point for frequency and set point for load. How much power do we need to disconnect? This is in percent to be more, relative units. And this is frequency. If frequency is lower than this value, we disconnect this. Here we see not one value like a set point, but we have two. We have two limits, upper and lower limit. Why? No, this is because we use for set points this block for Simulink with upper and lower limit. What is the idea? Why do we use this block? So physically, frequency drop, set point, frequency set point, signal to disconnect load. Load is disconnected. But this is a model. And frequency can go up, go down, go up, and go down. And to avoid the situation that this model disconnect the same load several times, that physically is important because we can only once disconnect this load, yes. But to design this idea in Simulink, we use this type of block with upper and lower limit. Just to avoid, as I said, that if we just here use the transfer function with a set point, okay, like greater than, logic block, yeah, to compare frequency, because here is the block input, this is block input, we got frequency for an input, yes, and if we have frequency lower than a set point, then disconnect. So it could be very easy, but in this case we need to put an additional mechanic that we can't disconnect this load more than one time. That's why we use this type of block. What else? Delay. Everything, this is switch, this is what we disconnect, this is the set point. Everything is very the same. Yeah, this is end block. Delay block. No, to make this block operation more realistic, because we understand in real life we have a delay because we have signals, we have operation and so on. That's why we put this block in for every stage, yes, artificial delay, yes, just to make this model more realistic. And every branch from this scheme is a set point. So frequency set point, how much we disconnect. Frequency set point, how much disconnect. So you need to design this frequency and to design set points. Here is an example with 10 set points, different frequency. This is stage number, load, power, and frequency set points. Just an example. Your task is to design your set points and design your number of outdoor frequency automation stages, to analyze your choose and to find the best set points and the best design for this automation. Okay, this is about the block number 5. And the last one, when we make the scheme once more realistic, because as we discussed, this is very quite rare when in a real power system, power generation is represented only by a one type. That's why this is the solution how we could make a scheme for power system with different type of power generator. This scheme is still a concentrated. Yeah, we unite like one node all power, but we separate these types. So this for CHPPs, this is for hydropower. If we have any other, we could put in parallel because this is a bus, yes, and we connect this in parallel, yeah. What is very important, don't to forget still to use saturation, because using this saturation, we could say, for example, we have power system with 70% of CHPP and 30% with hydro. And this saturation helps us to how to say, to put this structure of power generation into this scheme. So these saturation blocks could do this. For a very simple way, we could, how to say 50-50. So half CHPPs, half power. Okay. This is described here. So yes. Okay. So what to do? What to do to highlight? You need to make 3 models as it is here. So with only CHPP, with only hydro, and mix it. 3 models. You need to design this automation for every model as it is represented in every picture in the figure. You need to put set points. You need to have different outages scenarios for every scheme. So different. With different power outages, with different series outages. You need to make print screens what is going on with frequency here. This is a scope for frequency. And this is the scope what your under frequency automation is doing. Here we see in this scope steps of operation. So in what time, what stage was used. And you need to write an analysis about the situation, about this scenario, about the under frequency automation operation, what is good, what is not good. And final results, you need to choose the best set points and to prove your set points. That's all for the last year, how to say, individual laboratory. When you have only the first 3, your knowledge and time to play with Simulink with schemes. So, and as it was asked previously, yes, you don't have a ready-made scheme. You need to design it by yourself and to make it by yourself. Any questions? Okay, so this is all from my side for today about the laboratory number 4. But the next time we are going to talk about more advanced scheme, about how to model. This is not okay. This is the last task for you, what you had done. The next time what I'm talking about, we will discuss about this theory, about the model. I will show the model. I'll show you operation and results. Yes, just we will talk about the situation, about these faults, about what's going on when we have a frequency rise in one part of power system and a frequency drop in another one. We will see examples, for example, when we have in parallel different interconnections, as it is in Italian blackout, as we discussed, yes, in the year 2003. And we see what will happen, for example, if we disconnect one line that connect different parts for power system. If we disconnect two lines, what is going on with frequency? What is the frequency drop speed? So this will be, how to say, the lecture with schemes, modeling and example, but like a theory. For you, the last task that you should do by yourself is this, number 4. So as I said, welcome next time for the lecture, for the theory. And for task number 4, I said everything what I wanted. So I'm free to, how to say, to hear your questions. If not, we could close our, how to say, online part. Okay, so I stop the record.